So, hi everyone. So, today I am going to talk about Gauss Divergence Theorem, so which is a very important topic in vector calculus, right. So, Gauss Divergence Theorem is very important, and divergent is the concept in a vector space. And so, the statement of the theorem is, so double integral over s vector s f dot n cap ds is equal to triple integral over the region closed region B is equal to delta dot f vector dv. So, here this S denotes the surface and the capital B denotes the closed region capital B. And here we have a problem. So, verify Gauss divergence theorem for f vector equal to x square minus yz I vector plus y square minus zx j vector plus z square minus xy k vector. So, where this x values are from x equal to 0 to x equal to a, and y is from 0 to y equal to b, and the z values are z equal to 0 to z equal to c. So, this is the given problem. Okay, so the proof of the problem, we write the first statement of this double integral over s f vector dot n cap ds is equal to triple integral over v divergent of f vector and dv. So, we take the left hand side of the statement, which is double integral over s f vector dot n cap ds. So, here this f vector is the given vector and n cap is the perpendicular vector which is perpendicular to the field what we take, and ds is the double integrand. Okay, that also depends on the phase which we are going to take. Okay. So, here we draw the diagram of the given data. So, x is equal to 0 to x equal to a, and y equal to 0 to y equal to b, and z equal to 0 to z equal to c. So, we mark the x, y, z axis, and this line that denotes the positive side of x axis. So, here we have y axis and z axis respectively. So, this is the origin point we have. Okay. So, if you look at this problem, the x values are from 0 to a, right. So, here we have the point a, and here we have b, and then this is c. So, the coordinates are a 0 comma 0, here it is 0 comma b comma 0, and here we have 0 comma 0 comma c. So likewise we have the coordinates of the cube. So now we are going to start with this left hand side, that is double integral over the surface f vector dot n cap ds. So this is equal to this is equal to, so this double integral involves how many faces we have in the diagram. So totally how many faces we have? We have 6 faces. Okay, so we ordered them as S1 f dot n cap ds plus S2 f dot n cap ds plus S3 f dot n cap ds, and then S4 and then S5 f dot n cap ds, and the last one is along S6. Yes. So first, if we take this S1, S2, S3, S4, S5, S6 in order, we can take them like S1 is the field, the phase which is under this x and z axis. Okay. So I am taking this S1 surface as so for our convenient, we label the vertices as OA, BC and then DE, FG. So this S1 I am taking it as the surface which is OA and then ED. Okay. So this bottom surface is taken as S1 and S2 can be taken as which is above this surface, okay, which is parallel to the surface, that is BCGF. Okay, and we have the third surface which is S3. So we can take the surface which is parallel to y and z axis, that is OCGD, and parallel to that surface we have BAEF. So we have taken this bottom and the surface which is above that, and we have taken this surface and this surface. So the remaining two surfaces are the BC OA surface and FE DG surface, right. So we also take them. So S5 that denotes BC OA, and this S6 that denotes, that is parallel to this BC OA, which is FG DE. Okay. So this is how we take the surface as S1 to S6. Okay. Now we have to perform this double integral using all the surfaces we have taken from S1 to S6. So to perform that double integral, we can go for the table which is having serial number and then the surface, then the phase what we take, and then the n cap which is perpendicular vector, and then the integrand, that is double integral ds then we can go for the equation of that plane, then the integral value. Okay. So, first I am taking the surface S1, so which is this OAED, right. So, that is the face we are taking, and the perpendicular vector to OAED surface is minus j vector. So, we have two perpendicular vectors acting along those curves, that is y axis and z vector along it, and when you take the bottom of that face, minus j vector will be acting on it. So, we take this minus j vector, and the integrand for this particular face is, so when we take this minus j vector that is acting along y, so we have to leave that integrand. So, we are remaining with dx and dz. So, the equation for this plane is, that is we have this OAED, which is perpendicular to y axis. So, we have y equal to 0, which is the equation of that particular face, and we have the integral value. The integral value is like double integral f dot n cap ds. Okay. So, this is the integral value. So, this double integral f dot n cap ds. So, this n cap we have taken as minus j vector. So, f vector is this one, x square y z I vector plus y square zx j vector plus z square minus xy k vector. Okay. So, when you multiply this f vector and this minus j vector, okay, so when you multiply them, the coefficients of this j vector and j vector will be multiplied. So, here we do not have the I vector value and the k vector value. So, that will become 0. So, you multiply this y square zx and this minus 1. So, which will be double integral of minus of y square minus zx, and this ds is already we have taken here, which is dx and dz, right. So, the x limits are 0 to a and z limits are 0 to c. So, now we have to integrate this. Also, we have to put this equation, that is y equal to 0. So, when you replace this y equal to 0, this becomes, here this y square will become 0, and we have simply z and x. Okay. So, this is the simplified integral of this, and when you integrate this further, we can integrate x with respect to x, that is x square by 2, and z with respect to z, and that is z square by 2. So, it becomes so, when you apply the respective limits 0 to a to x and 0 to c to z, it becomes a square by 2 and c square by 2. So, on the whole it is a square c square by 4. So, this is the value of the first surface, that is S1, and we can continue with the second one, which is S2. So, S2 is above this x and z axis. So, we have taken BCFG. Okay. So, this BCGF is taken as the surface 2 S2, and the vector perpendicularly acting along in it is this j vector, and we have dx, dz, and then the equation of that is y equal to b, and we have this double integral. Again we will be having the same terminology, minus sorry, instead of minus we will be having plus j vector here. So, when you take S2, the plus j vector will be perpendicular to the S2 surface, and this y equal to 0 will be changed into y equal to b. Okay. Now, we are multiplying them and we will be taking this y square minus zx and then dx dz from 0 to a and then 0 to c. So, now when you start integrating, we have to apply the value of x y equal to b here. So, by continuing this calculation, we can write it here. So, when you integrate this b square with respect to x, we get x b square minus z x square by 2. So, with the limits of 0 to a. So, we are applying this 0 to a in this integrand. So, here we have a b square minus z b square by 2, and when you apply this 0 in both the terms, they are resulting into 0. So, we are just leaving them, and when you start integrating with respect to z, it becomes a b square z minus z square b square by 4, and it is from 0 to c. So, by solving this, we can get the value of a b square c minus b square c square by 4, right. So, this is the value we are getting, this a b squared c minus b squared c square by 4. So, by continuing this way, we can fill up the other surfaces S3, S4, S5, S6. So, when you take the third one, the surface is S3, and the third surface we have taken is this one CGOD. So, this is the face we have taken, and the n cap for that particular surface is acting along parallel to the x axis. Okay. So, we have to take this minus I vector, and the equation of that is x equal to 0. Sorry, the ds integrand is dy dz, and the equation of that is x equal to 0, and we have the integral value is f vector ds, f vector is this, and n cap will be this minus I vector, and the equation is x equal to 0. Yes. So, when you multiply them, okay, so when you start multiplying f and n, this I and I coefficients will be calculated, and also you are replacing x equal to 0. So, simply we get this minus also will become positive when you multiply. So, we get y z and then dy dz with the limits of 0 to b and then 0 to c. So, now we can start integrating this, we get y square by 2 from 0 to b and z square by 2 from 0 to c. So, when you apply the limits of this, we get b square c square by 4. So, this is the surface value of this S3. Then we take the fourth one, which is S4, as parallel to the above surface. Okay. So, we take this BF EA. So, here we have this perpendicular vector acting along this x axis is I vector, and the integrand is dy dz, and the value of this equation is x equal to a. So, this double integral will be, so here we have plus I vector, and the equation of this is x equal to a. So, this double integral value will become, we replace x equal to a here. So, it is a square minus yz of dy dz, and it is from 0 to a, and then it is from 0 to b and then 0 to c, which are the limits of this y and z axis. So, by solving this, we get a square y minus y square z divided by 2. So, with the limits 0 to b in this, so when you replace the limits here, it becomes a square b minus so again when we integrate this, okay, so with respect to z we are going to integrate. So, it is a square b z minus a square z square by 4, and you apply the limit which is from 0 to c. So, we get a square b c minus a square c square by 4. So, this is the answer for the surface S4. So, now we are going to take the other two surfaces. So, the surface 5, so which is we have taken this OA BC, S5 surface is this OA BC, and the perpendicular vector acting along that surface is minus k vector, and the integrand value is dx and dy. The equation for that is z equal to 0, and we have to calculate the integral value. Okay, so, integral value f vector dot n cap ds, and here we have the same f vector, but this n cap is minus k vector, and the equation is z equal to 0. So, when you start multiplying this f and n cap, we get the coefficients of k vector and k vector. So, other two terms will become 0, and also we replace z equal to 0 here. So, finally, we get the integral value as double integral x y and then dx dy from the limits of 0 to a and 0 to b. So, now if we start integrating this, so by the previous surfaces, okay, we will get the same answer, which is x square by 2 from 0 to a and y square by 2, and it is from 0 to b. So, by applying the limits, we get a square b square divided by 4. So, when you go for the sixth surface, which is the last one, so S6, and the plane we have taken is parallel to the last one, which is this FGDE. So, for this, the perpendicular vector is k vector, and ds is dx dy, and this equation is z equal to c, and the integral value is double integral. So, when you start multiplying, it becomes z square minus xy. So, we get c square minus xy, and then dx dy. So, with the limits of 0 to a and 0 to b. So, now when you start integrating this, it becomes c square x minus x squared y by 2 from the limits 0 to a, and here we have the limits of integral from 0 to b, and again we have to integrate with respect to y here. So, it becomes c square we have to apply the limit here. Yes. So, when you integrate with respect to y, it becomes y and then a squared y squared by 4, and it is from 0 to b, right. So, applying the limit, so we get a b c square minus a square b square divided by 4. So, this is the surface integral for the surface which is S6. So, now this left hand side is equal to this double integral f dot n cap ds along the surface S is equal to, which was divided into 6 surfaces from S1 to S6. So, for the first surface we have got the value of a squared c squared by 4, and for the second surface we have for the second surface we have taken this value ab squared c minus a square c square by 4. So, these are the answers for the first surface and the second surface. So, for the third one we have taken b square and then c square by 4, and for this and for the last two we have a square b square by 4 plus a b c square minus a square b square by 4. So, if you look at for the first term, we will have the counterpart in the second integral, right. So, we can cancel them. So, likewise we can cancel this, also we can cancel the last two. So, we will be getting the remaining as a b squared c plus a square b c plus a b c square. So, now in which a b c is common in all the three integrals, right. So, we can take them out a b c. So, if you take them out, it will be a plus b plus c. So, this is the answer for the left hand side and for the double integral value. So, now we have to go for the right hand side. Yes. So, the right hand side value was triple integral over the closed region divergent of this f vector over dv, or we can write it as this divergent of f vector is nothing but delta dot f vector dv over the closed region capital V. Okay. So, before going to this triple integral, we will calculate what is this delta dot f value. So, this delta is the delta operator, which is I vector dou by dou x, j vector dou by dou y plus k vector dou by dou z, dot product of this f vector x square minus y z I vector plus y square minus zx k vector plus z square into z square minus xy k vector. So, when you take a dot product of these two vectors, so the respective coefficients of I vector, j vector, k vector will get multiplied. So, we get dou by dou x of this x square minus y z plus dou by dou y of y square minus zx plus dou by dou z of z square minus xy. So, when you differentiate this, it becomes 2x plus 2y plus 2z. So, this is the answer for delta dot f vector. So, now we have to replace this value into the triple integral. So, now we are replacing it here 2 times of x plus y plus z, and then this dv is dx, dy, dz, and from the limits 0 to a, 0 to b, and then 0 to c. So, now we take this constant which is out of this, and we have triple integral of x plus y plus z. So, when you first integrate with respect to x, it becomes x square by 2 plus xy plus xz. So, with the limits from 0 to a, and dy dz is there, and we have 0 to b and 0 to c. So, 2 times of this 0 to c and 0 to b is there. So, when you apply the limit, it becomes a square by 2 plus a y plus a z, and we have dy dz. So, we can integrate this whole function as with respect to y, we get so this a square by 2, when you integrate with respect to y, it becomes a square y by 2 plus this can be integrated. So, this becomes a y square by 2 plus the last term will become a y z, okay, and it is from 0 to b, and we have dz. So, by applying the limits here, we get a square b by 2 plus a b square by 2 plus a b z, and we have dz. Yes. So, when you start integrating with respect to z, it becomes a square b z plus a b square z by 2 and plus a b z square by 2 with the limits 0 to c. So, by applying the limit, we get the answer of yes. So, 2 times of a square b c plus a b squared c plus a b c square. So, this can be written as, so in every denominator we can cancel them, and by taking the common term a b c, we will get a plus b plus c. So, which is the value of this right hand side. So, already we have the same left hand side, right. So, now we can write it as, so both the integral value, surface integral is equal to the volume integral. So, the main application of this Gauss divergence theorem is this. So, we can get the relation between surface integral and the volume integral. So, I hope this you can understand this concept very well. Okay, so we will meet in the next video. Thank you.